inculcate from the day we discovered like this program and all, like Ram sir and director sir and all have already undergone these trainings. So from that point onwards itself, I think this kind of changes has been already coming slowly into the curriculum and all the things we are doing.
Yes, in my family and in the circle, I see a lot of graduates passing out. So when I get a chance to them, I grab hold of them and I tell them this. See if you can address these three areas, and it's going to be more fulfilling. What you studied to work in that area, and to also see to that you also remunerate yourself well, because that's also the need of the hour. We all live in the materialistic need of the world, and to also give something back. Not to just. I think third point is something I want to emphasize, because I think the world already has a lot of capitalistic business organizations and people. I think the world needs now something what the course is offering, to become more mindful about the people and the energy or the resources that we consume from the planet. I think if that gets embedded in the educational level, I think it's going to be more impactful, rather than, because as somebody told in this forum, of late I'm becoming a chief education officer across all my, this is, I take more time than the business to talk about these things.
Okay.
Hello.
Mr. Murugan, one more point I wanted to end in the session was to take the feedback from the industry.
Hello.
My voice of the industry is, I think the new grads or the undergrads coming out into the market for jobs, I think emphasized, with the idea that there is no shortcut for success.
Yes,
it is true. We are a lot of engineers who comes to me, a lot of interviews that I do for engineers, they try to carry forward some idea of something happened with somebody, like they grow exponentially in 1 year, they got a fantastic job offer on day one, and and they don't have the patience to hold on to
more focused on weak continuous monitor measurements. And this we get H from IIT Dharwad. He is already having a few sessions earlier, and as I told you in beginning, most of the today talks, they will be based on this quantum measurements. So earlier sessions, they were more on introductory part, and now we are starting in with the quantum measurements. So maybe tomorrow also we will have some talks that will be related to the quantum measurements. So I hope every participants, everyone, they are already well aware with the sir, Dr. Babu sir. So without wasting any time, if sir is ready, I will request him to please give the talk.
Thank you very much, Avasti sir. I'm sorry, there was another meeting going on.
That I realized.
Multiple windows were open, so I was not sure where I was muting, where I was not muting. But anyway, I hope no damage done. Yeah, I did saw there was a session going on, so I hope Avasti sir gave a break for the participants after the session.
So this was, I think, by Dr. Jaskaran Singh from IIT Mandi on this quantum measurements.
It was supposed to be in the morning, no, sir?
It was supposed to in morning, but then we shifted it so that for staff and other members they will be available. Otherwise, being a Sunday, they are coming morning and then they are closing and coming evening.
Understood.
So this was the reason to shift it.
Understood, sir. Understood. Understood. Okay. Okay.
So
Yeah.
can
Okay.
you please give assist, sir?
I think we can start, sir.
Yes, sure, please, sir.
Okay, great. So let me share the screen. Sorry.
Sachin, please give the assist to sir. Okay, thank you.
Right. So yeah. Hello everyone. Very good afternoon. Sorry, good evening. Yes. Great. So
Perfectly visible and audible, sir.
fine. Thank you, sir. Yeah. So what we shall do is, as usual, we'll go back and forth between PPT and the Blackboard notes so that I can explain elaboratively. Okay. So I was looking at your this flow of this QT-07. Okay. So if I see here, what I see is there is introduction to quantum measurements by Dr. Jaskaran Singh. It was done just earlier. Okay. Probably projective and orthogonal measurements was introduced, and approximate non-orthogonal measurements were introduced. I hope so. Okay. Right. So just for the continuity for my topic, which is weak continuous measurements and error disturbance relations. Okay. Right. Since we have close to 2 hours time, we can go slow. It's a very, very important topic in quantum mechanics or quantum physics. Okay. So let's understand one thing first. What is quantum measurement? Probably it might have been addressed. Okay. Quantum measurement has been touched upon already. Okay. But for the sake of others, okay, so let me bring from my perspective what I want to be understood from the quantum measurements. Okay. Right. So I'll just try to connect to the real scenario. Remember, we are not supposed to connect the quantum mechanics or quantum mechanical phenomena which takes place at microscopic level to a macroscopic real world. We are not supposed to do that. You know why? Because the microscopic domain, let me write down that. The microscopic domain is dictated by or described by, I will say described, right? The laws of quantum physics. Okay. On the other hand, the macroscopic, the real world, people also say the classical world is dictated by, or I would say again, described by what? Newtonian laws. Newtonian laws of physics. Okay. For the sake of revision, I'll just say what are the Newtonian laws of physics. Newton's laws, the first law, what is that says? If something exists in the form of rest or in the form of motion, it tend to continue the same thing until somebody comes and disturbs it. Okay, it is acceptable because as per the intuition, it is fine. So it is called inertia, the law of inertia. It could be inertia of rest or inertia of motion. Means inability of something to change until some energy supply of energy or some intervention happens or not. So that is the first law for you. And the second law is very important. If there is an object of mass m, if you exert a force m on the object, you are going to generate an acceleration on the object. It is just like if you have a table, you are going to push that with some force. Depending on the size of the table, how much acceleration you can generate is decided. Okay. So again, straight away, a very good question is popped up here by Dr. Rajesh. The intervention should be external to the object. Is this true? Absolutely right. The intervention should be coming from external means. The intervention is within the system. I do not worry. Within the system, there may be mixing happening, some interchanging of energy may be happening. So for me, if on a macroscopic level, I don't see what goes inside atomic level. I don't see. Okay, I see only at macroscopic large level. Okay, so definitely you are bang on right. The intervention should happen from external means, which is a force. We exert some force and move the object. This is straightforward. It's a second law of Newton's law. Okay, even you can go on to describe this in terms of differential equation. How? You take the force, mass, write the acceleration as second order derivative of time. See, immediately this has become second order derivative of second order differential equation. You can solve and you can find what is the velocity at a given point, what is the position of a particle at a given point, or particle in the sense the object of mass m at a given point. You can find all those things. Basically, we are getting the dynamics of the system in time, in space, using Newton's laws. Okay, and there is one more law Newton has given. What is that law? Is action is equal to reaction. Everybody knows this. Okay, the way we respect somebody, they respect us. Okay, action is equal to reaction. If something you start abusing somebody, they will start abuse back. Okay, so the same thing in the real world. In the same desk example, I was trying to push the desk. Desk is trying to oppose my motion because it wants to stay in a equilibrium rest position without being disturbed. It wants to stay in a rest equilibrium state. It don't want to move, so it is opposing. Since I'm stronger than this, so I push with more force. So I'm giving an acceleration against the wish of the desk. The restoring, sorry, the opposition would come from the desk because of the mass m, which is like a opposition for me to do some work on the system. Okay, so action is equal to reaction. So this is beautifully used by many applications. One of the powerful application, action equal to reaction, is the rocket propulsion. So we were able to send the spaceships even beyond our Earth geostationary orbit, even up to Mars. Okay, right. So we were able to reach the escape velocity, means we were able to get go out of the gravitational pull by the Earth. Okay, right. So again, there is one more question by Rajesh. They need to be opposite to each other and always. Absolutely right. So okay, so like even a real world example, while I'm walking, I'm pushing away the floor behind my feet away from me so that I go forward. Okay, since the floor cannot go, it's huge, so I am going forward. I'm pushing, I'm going forward. Okay, So the same way, the rocket propulsion, the burnt fluid comes down and it exerts a reverse force. So because of that, the rocket goes up. Okay. Yes, they're equal and opposite. Right? Okay. Fine. These are the Newtonian laws which will describe the real world scenario goes around us. Now, what I just said earlier, I'm going to give you a real world example which could be used not as an equivalent, which could be used as a analogy to understand what is going to happen at quantum domain, that is microscopic domain, when I make a measurement. Okay, right? Fine. So let me give a title for this discussion. So quantum measurement. Probably it is being already introduced. So I will say quantum measurement revision. Okay, very good. Okay. And there is another comment by Dr. Lakshmanan Rao, same as conservation of momentum. Okay, so conservation of momentum is something is even related to the second law of Newtonian law. F is equal to ma. In fact, force is equal to rate of change of linear momentum. Okay, so you can just show F is equal to d by dt into mass into velocity. Okay, right? So conservation of momentum means momentum cannot be created or momentum cannot be destroyed. It exists in some form somewhere. If it disappears at that location, it goes somewhere else. The same amount goes somewhere else. It is just like conservation of energy. Energy cannot be destroyed and created, means somewhere energy disappears, somewhere else it gets appear. Overall sum of the energy in the two different locations, if you add, it goes to be constant. That is what conservation. So here also, when I am walking or the rocket propulsion, the overall momentum of the entire system must be zero here, because the one is going down, the one is going up. The one is going down, you see, the speed of the rocket propulsion gases, burnt gases, is seriously too high, and their mass is probably is very smaller compared to the spaceship. Okay, that's why with the same amount of speed, maybe spaceship may not go, but it is going to a greater speed after it reaches and reaches. Okay, so here if you see, the momentum has a direction. One is in the opposite direction, propulsion is in the downward direction, and rocket moving in the upward direction. Overall sum is actually constant, but time being in this case it is zero. Okay, right? So that is how the conservation of momentum is actually inbuilt inside a second law of Newton's law. Okay, right? So again, there is a comment by here. Is the third law somewhat related to first law? Inertia of object gives rise to opposition and hence the reaction. Yeah, you are I think in a way right. See, all the three laws, I can relate all the three laws in a given situation. Okay, right? If unless something is disturbing the state of the system will tend to exist in the same form. Okay, so when intervention is coming, there is acceleration, there is comes a force, second law. Okay, and if you exert a force, there is opposite force on you, there is a third law. So basically in a given scenario, I can see all the three laws. Yes, there is a connection between all of them. So in a way, they are like interchangeably could be used to understand the dynamics of the system. Fine. This is a, even somebody who doesn't know any physics also, they inbuilt innately they know it. Okay, farmers who are illiterate, okay, so they still know this basic physics. They use liver technology to raise something without any effort. Okay, so right now, what I said again, let me reiterate. I'm going to give an example or a scenario which could be used to understand what happens to a quantum measurement when I make a measurement on a given quantum system. Okay, right? So let me take an example. Analog, let's say, let me take a classical analog. Classical analog. Okay, what I take is, if everyone has ceiling fans in their home, okay, we just see a fan is, just switch on the fan. Okay, let's take a rotating ceiling fan. Okay, you see the wings of the fan, okay, continuously rotating. So I see a fan continuously rotating. What I see, the wings appear to me like everywhere. Okay, the location of those fan appears to be like me, like everywhere. Fine, that is amazing, right? So initially they were only located at 3 points, all the 3 wings. Now they appear to be everywhere. Okay, right? So even if you ask a small kid, where is this wing is located, he will say it is actually appears to be like everywhere. It is creating some kind of blur image. So, and he also, you will say, I can't exactly point out where it is located. So it is somewhere everywhere in that entire 360 directions. Okay. Now, please don't do that. I'll tell you one simple example. You take a stick, abruptly you just poke into the rotation. Just to poke a stick abruptly. Okay. So it was minding its own business, rotating. So I'll just poke with a stick abruptly. Then what happens? The wings were supposed to exist everywhere by rotating, and abruptly they come stand still. Okay, right? They come stand still as if their state of rotation was disturbed by my intervention. Okay, so I'll tell you here what is going on. A given wing, okay, wing of a fan, okay, initially while rotating appears to be existing everywhere. Okay, right? Everywhere. When disturbed, or when disturbed by stake, okay, what is happening? Abruptly comes to standstill. Okay, so what is happening is, just give me a minute. Hello, yeah. Sorry. So when things comes to standstill, as if the wing is having many possible locations, here you see wing can exist in many possible locations. Now, because of I am disturbing its state of rotation, okay, wing can exist in many possible locations. Due to intervention, okay, right, lost all its many possible locations. Okay, and what happened? It lost all but one, where it is finally halted. Okay, you see, right? So which means fan rotated, finally came to halt at some point. Now, if I had to list down what are the positions, I will say roughly it can be in position 0 degree, 2 degree, 3 degree, and up to 360 degrees. After I disturb it, it falls to, let's say, some 37 degrees. One particular wing I want to concentrate on. Okay? The same story, it's just analog. If you go and apply to a quantum system, let me apply now. Now, let's consider a quantum state, or I will say a quantum system. Okay, I want to take a quantum system. What quantum system? What is the best quantum system for we can have? The most simplest generic quantum system I can have is a qubit. Okay, a qubit is quantum state alpha 0 plus beta 1. Okay, this is simplest and most generic quantum system. What it is saying is a given quantum state can exist in 0 state and also in 1 state in a given instant of time. Okay, remember, and moreover, it can exist in 0 with some probability, exist in 1 with some probability, because ambiguousness is there, because of clarity is not there. And so in such situation, what I will do, I just want to make a measurement on this system to find what is the chance of I am finding 0 when I make a measurement, what is the chance of finding 1 when I make a measurement. I will get that. Now the question is, how do I do that? How do I find? For example, again, get back to the classical real world scenario. Classical real world scenario. It's the best, which is easy for me to understand. Okay. Let me take a coin. Okay. Take a coin. A fair coin, let me say. Right? A 1 rupee or 2 rupee coin or a 5 rupee coin if you just take. If you take the coin, if you toss the coin, what happens? The coin is in the flight. Okay. Now, usually if you ask a question to some small school kid, what is the chance of I get a coin after tossing? If I catch it, what is the chance of head? He will say simply 50% chance you have getting head, 50% chance you are getting tail. What he mean by that is, if you perform the experiment like for 100 times, out of 100 times, you will be getting 50 times head, 50 times tail. That is the meaning of that probability there. Okay. The sum of the both the scenarios should sum to 100%, where head comes 50 times, tail comes 50 times. Very good. That is understandable. Okay. Now, the same story would apply. Head comes 50 times, tail comes 50 times out of 100 tosses. Okay. Right. Now, same story for a quantum system which can exist in head and tail form. Now, you just think that qubit as a quantum coin, even a quantum coin. Okay. In fact, there is a notion qubit is termed as a quantum coin. Now, if you just take this coin, if you toss the coin, it exists in both 0 and 1, 0 and 1. So basically what I'm creating, I'm taking in the lab the quantum state of an electron initially was put in the ground. I am making somehow by supplying some energy, put the electron in the excited state for let's say 1 microsecond. After the 1 microsecond, it comes back. The moment it comes back, I'll send one more photon exactly 1 microsecond apart. Yesterday we discussed this. So basically, I am putting the electron back into the 1 state. Okay. And it does back and forth continuously. which is equivalent to having electron doing a Rabi oscillations between ground and excited. This is just like a fan rotating between 0 and 1 locations only. So here I can't use a fan analogy because fan has all the continuous existence of 0 to 360 degrees. But here in this case, the electron has only two possible locations, 0 and 1. Somebody may ask me, what happens to the level 2 and level 3 and level 4? It's a very valid question. You can still ask. Remember, as a theoretician, we can have a condition saying, I'll only consider 0, 1 by using something called selection rules. Okay? As per selection rules, I'll say selection rules. Okay? What I mean by selection rule is, I only take 0 and 1 in such a way that the other states doesn't come into the picture, into consideration, because the amount of energy of a photon which I'm sending only matches with the energy separation between 0 and 1. So if that trick if I follow, I'm only considering 0 and 1. Remember, why not 1 and 2 coming into the picture? Because their energy separation is different as per the real world naturally existing atom. Let's say artificially if I create a qubit, it's called transmol. Yesterday we discussed using LCR circuit with Josephson junction using. There I'm creating unequal energy separation between the existing quantum states of a qubit or any quantum system. Okay. So now using selection rules I can do that. Now the quantum state of an electron exists in 0 and 1 parallelly or simultaneously. Now as an experimentalist, what you can do, you want to know, if I toss this quantum coin and catch it, how many times you will find in ground, how many times it finds in excited. That is a very important things to have. Okay, because you want to get the insight out of the quantum qubit. Okay, now for that you have to make something called quantum measurement. Quantum measurement, right? You have to make a measurement. If you want to find what is the temperature of some patient as a doctor, you need to find a thermometer and put in his mouth or in this between his arms and then find out what is the temperature. Okay, right? You need a measuring tool. Obviously, I need a measuring tool here. Okay, so the question is, how do I create that measuring tool? Is there any particular thing which measures? Okay, of course, there is a interesting measuring tools. Probably it is being introduced already. But let me introduce from my perspective, what is this measurement tool? First of all, to know about the measurement tool, okay, to know the temperature of a person, I should know what is the right measurement tool to measure the temperature. You see, if some person has some kind of a BP issue, I am not supposed to use a thermometer and go and find his blood pressure using thermometer. It's a wrong tool. Okay. First of all, I should know what I'm measuring. Okay. I'm measuring whether the temperature is between 97 degrees Fahrenheit or 98 or 99 or 200, sorry, 100, 101 and so on, right? Okay. So I need to have a right tool to measure the whatever I am intended to measure. Now, before measuring, I should first find out what I'm measuring. So if I have my quantum system, remember I'll bring a not a new concept, a fancy concept, where you see this quantum state is defined or described on what? A basis of 0 and 1. Okay? 0 and 1 is also called computational basis. Okay? Basically, it is being used for computation. Probably that is how maybe it is being named. 0 and 1 is a computational basis on which this quantum state is being constructed. Okay, this is just like in our real world scenario, a two-dimensional Cartesian coordinate system, which Cartesian coordinate system helps me to describe a position vector of any particular point in that surface of a two dimension. Okay, ing are the unit vectors which helps me to do that. Okay, we know that. Fine. Now the question is, the computational basis vector I at 0 ket and 1 ket is there. Now I want to find out what is the probability of finding given quantum state in 0, given quantum state in 1. I want to find out. Okay. And now when you come back to a two-dimensional system, you see the two-dimensional vector is there, xi plus yj is there. Now there I see the r vector, how well it is flowing along the x, that is I cap direction, how well it is flowing along the y direction, that is the j cap direction, is conveyed to me by the values of x and y. You see, beautifully I know values of x and y. Now, how do I find in this particular case? Let me just take that analogy, a little bit extended analogy. That way you can appreciate what exactly being done in quantum computing. Now, if I want to know how much strength, means how much well the r vector is flowing along the I direction, how do I know? Just take I vector, multiply to the r vector. What do I get? X is a constant, I dot versus I dot plus y, I dot versus j dot. There's a dot product. You remember? I'm taking a dot product. Now, as you know, I dot I is 1 plus y dot I dot j is 0. So I'll have 0. So what it is giving me? It's giving me a value of the constant. Okay. So the value of this constant x is telling me how much well together r vector is going along the I direction. So this was the idea. Similarly, you can use j dot r gives me x j dot I plus y into j dot j, where j dot I is 0. They are orthogonal vectors. I and j into j is a dot product is 1 because they are also normalized vectors, means unit vectors. I'll get 1 here. So y here. So you see, by taking a dot product, the tool I am using here is taking a dot product of those base vectors. You see, that's a catch is important here. The base vector is telling me or helping me to find out how much well the r vector is flowing along that base vector I and j. Okay, so can we use that kind of a technique? Question is, can we use the same technique, okay, for quantum systems? Okay, it is fair to ask, right? It is being earlier, it was also told the quantum state of a qubit is like a two-dimensional vector equivalent to or analog to a two-dimensional position vector in a Cartesian coordinate system. Okay, fine. So that means whatever they were doing there, can I do it here? That's a fair question to ask. Of course, the answer is yes, possible, but may not be exactly possible. Okay, so let me try that. I have a quantum state beautifully, which is like this. Now I want to find what is the chance of system finding in 0, means how well quantum system is flowing along the 0 direction. Let me take the product of 0 with a quantum state. Remember, quantum operations, how do we take a quantum operations? We put them in the bracket. The actual operation would be a matrix multiplication, where the left entry becomes transpose and the right entry remains as it is. Let me do that for you. What I'll have, alpha 0 plus beta 1. Okay, what do you get? Alpha is a constant, 0 inner product with 0, beta 0 inner product with 1. As we know, 0 ket is matrix wise 1 0, 1 ket is 0, 1. So if you see, inner product between any two same vectors is 1. Inner product between unlike vector is 0. What do I get? I get alpha. Oh, that's amazing. I'm able to get the same way. How much? Well, it is being flowing. Now, so earlier, when I'm multiplying I with r vector, okay, the state of the system is remaining intact. It's not going to disturb. But when it comes to quantum state, what is happening here is, just like the fan analogy which I gave you, the quantum state is actually falling into one of the state. Okay, the moment I catch the coin, what is happening? Coin is no more rotating, no more in the flight stage, so it is lost to one of the fixed state. That is happening in the real world, also happens in the quantum state. So you can say, conclude, okay, conclusion, measurement, very important, measurement, okay, takes place with the, okay, let me write down place also, takes place with the collapse of the quantum system. Okay, its collapses. So quantumness is no more there. Fan is rotating, even though power is supplied. When I poke with a stick, it is no more rotating. Okay, right? So that is beautiful. Now, I can also find what is the chance of quantum state being found in Ket 1 state. I can do that. So which gives me 1 beta. Okay, this is fine. Now, the question is, on paper I am doing it. Okay, when it comes to the experimental case, the real world scenario case, what is this multiplication is about? Okay, for an experimentalist, he can't write everything I experiment on the paper, right? He will do literally in the lab. Okay, so for him, how do he finds this alpha and beta values? Okay, so there will be some kind of a probe he will use, just like a thermometer. He will use, okay, to find the temperature. He will use, what is that probe would be is, remember now I'll tell, the probe, or it is called the projection operator. Okay, so why the name projection operator is, see, for us projection means what? We use projectors. Okay, we use projectors, we project something onto a screen, right? So the projection operators are just similar to that. They project something from somewhere to somewhere. Okay, right? So then let me take a small question here by Rajesh ji again. If a quantum state is represented as a vector, does it have a direction too? What analogy we can have in quantum related to classical vectors like velocity, etc.? Very, very valid question. Okay, right? So vectors for me, what? Vectors are the ones which has a magnitude and the direction. Okay, so in real world conventional scenario, vector has a direction and magnitude for sure. The position vector means from particular point, a reference point, how far the object is displaced, in which direction it is displaced is actually told by the direction. How far it is displaced is given by the magnitude. Agreed. Let's say something is moving in a particular direction with particular magnitude of velocity. Okay, so the direction of the velocity is actually speed, okay, with which it is moving, and the direction gives, okay, that is also a valid thing. Now Chauhanji was asking, Churasiaji was asking, Rajesh Churasia, does quantum state as a direction? Okay, remember quantum state existing in a direction means, okay, a two-dimensional vector, if you just take a two-dimensional space, a given vector is pointing along particular direction in a 2D surface. So it is existing in a a 2D surface represented by a vector space, okay, 2D vector space, where this R1 is among many vectors, not only starting from center, it may start from somewhere, but I'm just only drawing from the center. You see, this R vector is one among many, okay, where many of them are pointing in different directions. Now the question is, so the direction of this R vector, maybe there may be vectors of same length, but the direction is different. So that is how we know R1 is how it is unique from the other things. Okay. The same thing in the case of blocks, in the case of quantum vector state, alpha 0 plus beta 1. Does it has a magnitude? Of course it has a magnitude. What is the magnitude? Let me find the norm of this vector, which is simply absolute alpha square plus absolute beta square. In fact, it is a constraint for a quantum system. Okay, we're talking about an electron being in a ground and excited. Those are the only two possible locations for it. Means it has to be either here or there. So, or it can be a combination of probability sum. It should sum to 1. So, it has 100% probability. So, overall length is 1. Okay, it has length, that is unit length. Okay, unit length. Now, what is its direction? Okay, where it is pointing out. Now, in order to have a direction, in order to represent a direction means what? Why do I need a direction to something? I want to geometrically interpret something. Okay, if somebody is going in a ground, okay, you ask your friend, where is he going? You will usually say, he is going towards a canteen. He is going towards some other hostel building. Okay, so you are giving a direction, and you also give, he is moving with very fast speed, so he is running. Okay, so basically you are giving extra information. Here in this case, the quantum state is uniquely different in a direction with respect to other quantum states. Geometrically is different by taking a direction. Now I don't see any direction here. How can I understand the direction? Remember, for the geometrical interpretation of a qubit, the people of quantum computing, the developers, they gave, luckily for us, something called block sphere representation. So what they did, they took a three-dimensional polar coordinate system. You remember, 3D polar coordinate system, where I have r cap variation, theta cap variation, phi cap variation. R cap is distance from the center. Okay, right? How it is varying. Okay, and theta cap is, if you just have a vector, so theta cap makes an angle theta with the north pole. So if I have I cap and j cap and k cap as a Cartesian coordinate three-dimensional system, okay, I'll use the both polar and Cartesian to describe a given vector in a three-dimensional surface, where you see the given r vector makes an angle theta with a z-axis, and if you just drop a light from the top, okay, what it will do? It creates a shadow on the equatorial plane, so that equatorial plane makes an angle phi. So it's called azimuthal angle or equatorial angle. Now, any point in this three-dimensional surface would correspond some value of r cap, some value of theta cap, some value of phi cap. Now, as you know, all our quantum systems are of unit length. So what I'll do, I'll suppress the length of the quantum state to 1. Okay, I'll write still in terms of quantum classical vector. The moment you do, the free degrees of freedom of r cap is gone. Only I have theta cap and phi cap. So what I will do now, I'll just play a trick. What trick I'll do? I'll introduce alpha equal to cos theta by 2, beta equal to sine theta by 2, exponential I phi. If I introduce this trick, what happens? My quantum state now becomes the vector pointing in several directions in three-dimensional surface. What is this? It will be cos theta by 2, 0 ket, plus beta, sorry, plus sine theta by 2 exponential I phi, sorry, I phi 1 ket. Now you can say proudly, in a block sphere, I have a quantum system. Okay, I have a quantum system which is pointing along some particular direction with corresponding theta, corresponding phi. Remember, there may be several such quantum systems, infinitely many. Among them, this is the one quantum vector unique with respect to having theta and phi value. So the vector space in which it is defined is a Hilbert space. Okay, right? Yes, the answer to Rajesh sir's question is yes, quantum state has a direction. It is not like any conventional direction. To understand this direction, I need to give a geometrical interpretation using block sphere representation. Okay, yes, it has a direction. How? In terms of alpha and beta values, these values are actually captured. The direction values are captured. Okay, fine. Now, let's say phi is 0 means what? Phi, value phi is 0 means what? Okay, so we are not sitting on any points where there is a equatorial surface. Okay, phi is 0 means exponential I phi is 1. So only theta is the one which makes a difference for me. Now, if you just take theta is also 0, what it implies? Quantum state is actually 0. Okay. So the north pole is correspond to this theta and phi value both 0. And if theta is equal to pi degree radians, so then I will have quantum state becoming 1 ket because sine theta pi by 2 is 1, cos theta by 2 is the pi by 2 is 0. So I'll have south pole pointing along the z direction is 1 ket. Other than these 2 points, everywhere I see the contribution coming from theta and phi, contribution coming from the non-zero theta and phi, let me tell you. And the contribution coming from 0 ket and 1 ket contribution into the superposition. So I see the like some contribution from 0 ket, some contribution from 1 ket. So in that way, I can represent the quantum state in terms of its direction. And since I don't worry too much about its magnitude because always its magnitude is 1. It's a unit vector, by the way. Okay, fine. I hope I answered your question. And again, there is one more question. Difference between polar coordinate system and Gilbert space or Hilbert space. Yeah, it's a Hilbert space, not a Gilbert space. The difference between polar coordinates and Hilbert space. So polar coordinates are what? Okay, I'm sorry if I'm deviating too much, but it's better to clarify a few things here and there. Okay, so let me go from the simplest case. I have Cartesian coordinate system. Okay, Cartesian. Okay, so in the Cartesian coordinate system itself, let's say if something is moving away from the center, I'll call it as r cap. Okay, so let's say something making a circles, so it moves perpendicular to r cap. So that is what my theta cap. So let's move that vector. Okay, theta cap to the center. So vectors without changing its direction, I can move it. Nobody is going to object that. Yeah. Okay. So let me move that. So when I move it, the theta cap would be exactly perpendicular to r cap and theta cap. Now you see, I cap and j cap is a Cartesian coordinate system. R cap and theta cap is a polar coordinate system, which is useful when things are moving in circle. To describe them, I need that. How do I know in which direction he is making circles, from what distance with radius he is making circles? Okay, so for that I would be needing. So this is Cartesian rectangular system, or you can say that. Okay, this is polar coordinate system. Okay, now for 3 dimension, I'll take one more extra dimension, which is like this: I cap, j cap, and k cap. Now, in the case of polar coordinate, if I want to have a 3-dimension, what do? I use the Cartesian as it is. So I just take a equatorial plane, circular plane, and build a surface of, okay, something like that. Okay, let me remove internal. I have a 3-dimensional surface where any given to the surface point vector makes an angle theta. Equatorially, it makes the shadow of that angle phi. So I will have r cap, theta cap, and phi cap as a spherical polar coordinate system. Okay, right? Now, if you see, coming back to your question, difference between polar coordinate system and Hilbert space. So Hilbert space is the surface, the points on the surface of a block sphere is only connected to Hilbert space. Maybe let me remove the projection operator here, and we'll come to that. We'll conclude. Okay, so the block sphere, the points on the surface of a block sphere, okay, would represent, okay, would represent, not represents, would represent, okay, the quantum states exist in the vector space, which is named after Hilbert space. Okay, so now you can tell me the difference between the Hilbert space to 3-dimensional polar coordinate system is 3-dimensional polar coordinate system as an extra dimension of r vector, which is removed in the Hilbert space, because a Hilbert space is just a 2-dimensional system, okay, which is generated out of a basis of 0 ket and 1 ket. So it is just a 2-dimensional system. Remember, it can have as many as number of vectors. Okay, it can have any number of vectors. How? I can have alpha, beta, any number of values with a constraint of the summing to 1, their absolute square. I can have any number of vectors. Okay, so this is a 2-dimensional, means the basis has 2 elements. So Hilbert space and polar spherical coordinate system is different by 1 dimension. Okay, right? So if we are not supposed to compare them in that way, but just for understanding, I am telling. Okay, now what is one more question? The difference between theta and phi in block sphere. Okay, right? I see, if you go back here, theta is the angle between your block vector or a quantum vector to the z-axis or the k cap. Okay, so that is the angle theta. Now if you just shine a light from the top, that is going to cast a shadow. Maybe let me draw a bigger diagram. Probably you may understand that. Okay, I'll try to be a little bit neat now. Okay, so let me draw the nice circle. Okay, now you see, let me take a different color just for your understanding. I have a quantum state. Okay, let's say this is psi. Remember, I'm not going beyond the surface. It is on the surface. It doesn't mean the vector is inside, it is on the surface. It's a 3-dimensional picture. Now you see here, the quantum state is making theta with respect to k cap direction. This is I cap, this is k cap. Now if you put a light from the top, okay, what happens? This vector psi would make an angle in the equatorial plane. It's shadow. The shadow meets at this point. Okay, so the shadow makes an angle phi with the x-axis. So now you see, phi runs between 0 to 2 pi. You see, it can make one complete circle in the equatorial plane, and theta runs from 0 to pi only, because It doesn't have anything beyond that. Okay. So the difference between theta is a pole angle. It's a polar angle. Makes an angle with the polar north pole. And phi is azimuthal angle. It's a equatorial angle. It exists in the equatorial plane. Not only equatorial plane, any plane it can exist. For example, on this plane also I can have angle. Okay. So that is the difference between the theta and phi. Okay. So does that mean SP, SP2 and SP3 orbits represented by Hilbert space? Okay. Now, Hilbert space and the SP and SP2 and SP3, these are orbits in the case of solid state physics. You should not mix it up. Okay. Hilbert space is a vector space of quantum states. Okay. Right. Let me switch on the light. It's becoming slightly dark. Give me a minute. Okay. Right. Okay. Right. So some vehicle is okay. So yeah, Adogiriji, I think you should not mix up. I'm not getting exactly why do you bring SP, SP2, SP3 orbitals represented by Hilbert space? Okay, so probably what you mean is, see, orbits are what is the orbit for me? Orbit means it's a cloud, a region where the electron may exist anywhere in that particular orbit. That is the orbit for me. So sp2, sp3, sp orbit, they have shapes. Okay, within that cloud shape the electron may exist. It's a probabilistic location, I would say. Okay, right? So Hilbert space is okay. I think let me your context, let me understand. Does it mean sp2, sp3 orbits are represented? Okay, no. So Hilbert space is a collection of vectors, and sp2, sp, and these are the locations. Okay, probably inside this orbit there may be a points which are showed by a given vector from a Hilbert space. Okay, so they are a bigger domain. Sp orbits are a bigger domain, and Hilbert space is collection of few vectors which makes a vector space. Okay, fine. And yeah, the questions are popping up continuously. Let me give. I mean, orbital representation, hollow inside. The representation figures in textbooks. No, right? So inside the hollow region, there may be a vector, okay, which represents on the hollow region where the vector is pointing out. So we can't have the vector space representation for the orbits. Okay, if I am correct. Definitely, as per my base understanding, okay, we can't mix up. So orbits are actually coming up because of when I solve the Schrodinger equation, I'll be getting what is the absolute square of my wave function values for a given position, given time. So from there we'll get the orbital structure. Okay, right? Schrodinger equation solving, you get a orbital structure. Okay, right? So in the textbooks, whatever they showed is the solutions of a differential equation which dictates the dynamics of the quantum system. Okay, right? That's a Schrodinger equation for you. Okay, then there is one more. I have asked about couldn't we get the answer. Can you please help understand whenever we measure the quantum state collapses? So when and why do we measure? When will be the need? Okay, does measurement give the factual condition as it collapsing? Why practical means? Okay, I'll come to that. We are trying to answer that question. Okay, but increase in theta further leads to Rabi. No, increasing theta, no. Rabi oscillations, you mean? Increasing theta, it goes from 0 to 1. And if you have to oscillate the values of theta from 0 to pi, then only you will have oscillations, Rabi oscillations. Okay, I think Rajuji was asking that question. Can we observe and notice superposition? Yes, of course. You can observe I think Lakshmana and Rauji is pointing out. Yes, we can observe the superposition. How? Electron is making oscillations between ground and excited, or it disappears in ground, comes in the excited, disappears in the excited, comes in the down. So yes, this we can see, and experimentally Rabi oscillations were seen. People are experimentally seeing. Okay, yeah. Is it as it is collapsing? Can we physically observe the superposition by practical means? Okay, right. So straightforward, simple answer to this question. Like since many were asking, okay, so there is a technique called, that was the main theme of our talk today. So there is something called, either you can abruptly disturb the system and get the insight. Okay, right? So which means it is collapsing. I had to do this same experiment several times to get to know the coin is fair coin or not. If I toss a coin, so I catch it, while catching it is not destroying, so I toss it again. So in the case of quantum system, it is not the case. Okay. So what you can do is, okay, you just take a bunch of photons coming from a coherent source, right? So the coherent source photons, if you able to create a vertical polarization and horizontal polarization with a particular weights, okay, so you will be getting a stream of photons in this polarization. What you do, you make a measurements on all the photons several times repeatedly. By doing it, you will get what is the alpha value, what is the beta value. Okay, so in doing every experiment, photon polarization is falling into one of the case. Okay, but when I have a quantum coin, a quantum qubit, when I make a measurement, it is falling into one of the zero state, it is lost. I can't do anything more than that. For that, what people do, they do something called a weak measurements. Weak measurement in the sense, okay, if there is a qubit which I want to find what its state, so I'll have, let's say, some small test qubit, okay, small test charge, I just bring near to it. So it's called readout ion or readout qubit. Okay, and the purpose of this read is slightly go near to it and try to grab as much as possible without disturbing the state of the system. Okay, if that is possible, I can get essence of the actual qubit. But the problem here is I'm not getting the exact essence, because if I try to do it, I'm disturbing the system. So I'll make a several weak measurements on the system by such test charts, and I will do the statistical analysis. From there, I'll get what is alpha, what is beta. That is a weak measurement which I am performing on the quantum systems. Okay, just like a fan is being halting to one of the state, qubit which is making a qubit means a quantum uh, electron making oscillations between excited and ground. The moment I just make an observation, it falls to one of the state, let's say ground state. Okay, so that is what I would wanted to convey for today right now. So since it's already 5:12, we can take a quick break, and we'll come back. Okay.
Okay, thank you, sir. We will have 5-minute break, and then we will resume.